Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the SAC series.
It is wonderful to be back.
Today we are exploring the hidden world of catalysis.
A topic that sounds, I admit, incredibly technical, maybe a little intimidating.
It really does. I have to admit, when I first looked at the stack of research for this, my mind immediately went straight back to high school chemistry. I was picturing bubbling beakers, those uncomfortable safety goggles, that distinct smell of sulfur in the lab.
And memorizing the periodic table for a test you're probably cramming for.
Oh, definitely. I thought we were going to be getting into a very, very niche corner of science. Something for the specialists.
Instead, what did you find?
Instead, I realized we are talking about the invisible architecture of our entire modern lives. We aren't just looking at some abstract chemical process. We're looking at the silent engine behind civilization itself. That is the perfect way to frame it. A silent engine. It is one of those phenomena that is absolutely everywhere. It's doing everything, yet nobody ever talks about it outside of a chemical engineering lab.
Right.
If you look at the industrial data, the estimates suggest that 90% of all commercially produced chemical products, they involve catalysts at some stage in their manufacture.
That number just stopped me cold when I read it. 90%.
90%.
So that means if you just look around the room you're sitting in right now, or, the car you're driving, almost everything you see owes its existence to this concept.
Everything. The plastic in your phone case, the dashboard of your car, the fuel in the tank, the dye in your shirt.
Even the food in our stomachs, which we'll get to.
Even the food in our stomachs.
Yeah.
Exactly. Without catalysis, the modern economy doesn't just, slow down. It freezes solid. It stops.
Yeah.
We would literally be unable to support the population we have today.
So our mission for this exploration is to pull back the curtain on this invisible layer. We're going to look at the history, which is, I was surprised to find, surprisingly dramatic. We're talking literal life and death stuff.
Absolutely.
But we're also going to look at the future, which is it's getting very sci-fi, with artificial intelligence designing brand new materials to eat our own garbage.
We're going to span that whole arc from what was essentially the black magic of the early days to the digital design of tomorrow.
But before we get to the AI and the world-saving inventions, I think we have to eat our vegetables, so to speak. We have to understand the mechanism. Because the simple definition of a catalyst is something that speeds up a reaction without being consumed. That sounds simple, almost too simple. How does that actually work?
Mechanically, it's all about energy. The proper scientific definition is that a catalyst lowers the activation energy of a reaction.
Okay, let's unpack that term, activation energy. I feel like I know what that means intuitively, but could you break it down for us?
Of course. Imagine you're on a road trip.
Yeah.
You're in a valley, and your destination is in the next valley over.
Okay.
But between you and your destination is a massive, towering mountain range.
And the destination, that represents the chemical product I want to make.
Exactly. The product you want is on the other side of that mountain. Now, nature creates these mountains, these energy barriers, to keep things stable. It's a good thing.
How so?
Well, if there were no barriers, every molecule would just react with every other molecule instantly. The wood in your house would react with the oxygen in the air and spontaneously combust. You dissolve in your bathtub.
So stability requires these barriers. The mountain prevents chaos.
It does. It keeps the world from falling apart.
Yeah.
But sometimes we want to get to the other valley. We want to make something new.
Right.
And without a catalyst, the only way to get your car to the other side is to drive all the way up and over that mountain. You have to climb thousands of feet. That requires a huge amount of fuel.
In chemistry terms, that means what? Massive amounts of heat and pressure?
That's it. You have to force the reaction to happen by brute force, pumping in tons of energy.
And a catalyst, then, is what? A better engine for the car?
No, is something much cleverer. A catalyst digs a tunnel through the mountain.
Oh, I love that visual. That makes it so clear.
The starting point is the same. The destination is the same. But the path you take requires a tiny fraction of the effort. You don't have to climb the peak at all. You just glide through the tunnel.
So the catalyst doesn't change the end result. It just changes the journey. It makes it easier.
Precisely. There was a scientist, Wilhelm Oswald, a giant in this field back in the late 19th century. He actually won the Nobel Prize for this in 1909.
Okay.
And he used a few great analogies. He compared a catalyst to oil in a machine.
The oil doesn't power the engine.
No, of course not. The fuel powers the engine.
Uh-huh.
But if you try to run an engine without oil, The friction is so immense it just seizes up and grinds to a halt. The oil reduces the resistance so the work can actually happen.
That's a good one. What was the other?
The other was a bit more of its time. He used the analogy of a whip on a tired horse.
That one feels a little more aggressive, maybe.
It is, but it makes the point perfectly. The whip stimulates the action, but the whip itself isn't pulling the cart. The horse is doing all the work. The catalyst facilitates the change, but it doesn't become part of the final product. It walks away unchanged, ready to get the next reaction going.
Okay, so that's the what. Makes things easier, it digs a tunnel. But how does it do it? On a molecular level, what's happening? Does it just grab molecules and smash them together?
It's more of a gentle seduction than a smash. And this brings us to what is arguably the absolute core concept of this entire field. If you take one scientific idea away from our conversation today, let it be this one. It's called the Sabatier principle.
Named after Paul Sabatier.
Another Nobel laureate. This field is full of them. He's the one who first described what is essentially the Goldilocks zone of chemistry.
I'm familiar with Goldilocks. Not too hot, not too cold, but just right.
That's exactly it. In catalysis, it's all about stickiness. For a catalyst to work, the reactant molecules, your ingredients, have to land on the catalyst surface and stick to it for a moment. We call this absorption.
Absorption with a D, right? Not absorption with a B.
Correct, a very important distinction. Absorption with a B is like a sponge soaking up water. The water goes inside the sponge.
Yeah.
Absorption with a D is like a Post-it note sticking to a wall. It stays on the surface. That's where all the action happens.
Got it. So the molecules stick to the surface. What's next?
Well, here is the Goldilocks problem. If the binding, the stickiness is too weak, the molecules just bounce off immediately.
Like trying to stick a Post-it note to a wet window.
Perfect. Just slides right off. Nothing happens. Your reaction rate is zero. No tunnel gets built.
Okay, so you need it to be sticky enough.
But, and this is the crucial part, not too sticky. If the binding is too strong, the molecules land, they stick, they might even react with each other, but then they never leave. They're essentially glued to the surface.
They become squatters. They're just clogging up the works.
Exactly. They clog up what are called the active sites. The catalyst gets poisoned because there's no room for new molecules to come in and react. So, the Sabatier principle says the binding energy has to be just right.
Strong enough to hold the molecules in place while they react, but weak enough to let the new product go so the site is open for the next customer.
You got it. It's the perfect balance.
That seems like an incredibly delicate balance to strike. You're asking a material, a piece of metal, to be simultaneously sticky and slippery.
It is the fundamental paradox of the field.
Yeah.
And chemical engineers have spent more than a century testing millions of materials to find the ones that sit right in the sweet spot of that curve.
Now, looking through the research, it seems there isn't just one way to do this. There's a sort of taxonomy of catalysts: homogeneous, heterogeneous, and biocatalysis. I want to break these down because they seem to dictate how our factories are actually built.
They absolutely do. It's all about the phases of matter. Solid, liquid, gas. The first category is homogeneous catalysis. Homo means same.
Right.
So in this case, the catalyst and the ingredients are in the same phase. Usually this means everything is a liquid.
Like mixing a cocktail.
Exactly like a cocktail.
Or a soup. You dissolve your catalyst, maybe a metal complex, into a liquid solvent along with your reactants. Because everything is swimming around together at the molecular level, you get incredible interaction. Every reactant molecule can find a catalyst molecule easily.
That's very efficient.
Highly efficient, and you can get incredible selectivity. You can design it to make exactly the one product you want and nothing else.
That sounds perfect.
Yeah.
So what's the catch? Why don't we do everything this way?
The catch is getting the catalyst out at the end.
You can't unmix the soup?
Not easily. Think about it. If you're making a high-purity pharmaceutical drug, you really don't want the, say, platinum or palladium catalyst left in the pill you swallow.
Definitely not. But separating a dissolved liquid catalyst from a liquid product is an industrial nightmare. It often requires distillation, which takes a huge amount of energy, or complex extraction processes. It's very expensive and complicated.
Which explains why the vast majority of industry prefers the second type, heterogeneous catalysis.
The industrial workhorse. Hetero means different. In, I would say, 95% of industrial cases, this means the catalyst is a solid and the reactants are liquids or gases that flow over it.
So I should picture a big industrial pipe just filled with, what, metal rocks, pellets.
That's basically it. Picture a river flowing over a bed of stones. The water is your reactants, and the stones are the solid catalyst. The reaction happens at the moment the water touches the surface of the stone.
And the benefit here is immediately obvious. The water flows past, but the stones stay put in the riverbed.
Exactly. Separation is effortless. It's built into the design. You don't have to boil or distill anything. The product just comes out the other end of the pipe, and the catalyst stays in the reactor, ready for more. This is exactly what is happening inside the catalytic converter in your car.
Right, that's a thing people are always trying to steal from under cars.
Unfortunately, yes, because it's full of precious metals. The hot exhaust gases from your engine, full of toxic carbon monoxide and nitrogen oxides, they flow through a ceramic honeycomb structure.
Okay.
That honeycomb is coated with a very thin layer of platinum, palladium, and rhodium. As the gas touches the solid metal surface, those toxic fumes are instantly converted into much safer gases like CO2, nitrogen, and water vapor.
Now, you mentioned the theft. Platinum is incredibly expensive. I saw in the notes that these solid catalysts are often supported. They aren't just solid chunks of platinum, are they?
Oh no, that would be economically impossible. A solid brick of platinum would cost millions and millions of dollars. But more importantly, it would be incredibly wasteful. Remember, the reaction only happens on the surface.
So all the atoms buried deep inside that expensive brick are totally useless.
Completely wasted. They will never see a single molecule of gas. So engineers use what's called a support. They take a cheap, highly porous material like alumina or silica or something called a zeolite. Think of it like a sponge made of rock. It's riddled with millions of tiny holes and tunnels.
Which gives it a massive surface area.
An incredible surface area. A single handful of zeolite powder can have the internal surface area of an entire football field.
Get out! A handful! That's hard to believe.
It's true because of all the microscopic internal porosity. So you take tiny nano-sized particles of your expensive platinum and you essentially sprinkle them all over this high surface area sponge.
Wow.
You spread it out so that almost every single platinum atom is on a surface, exposed, and ready to react.
You're getting the maximum possible bang for your buck. That's incredibly clever.
It's the only way to make it affordable.
Okay, so we have the soup, which is homogeneous. We have the river flowing over rocks, which is heterogeneous. What's the third one? Biocatalysis.
Nature's catalysts. Enzymes.
So these are the originals, the OGs.
These are the absolute masters. These are complex protein molecules that evolution has been refining for billions of years. Your own body is full of them right now. They're digesting your food. They're replicating your DNA. They're running every process in your cells.
And industrially, we've used them for things like making bread and beer for thousands of years.
Fermentation is a perfect example. It's just yeast enzymes turning sugar into alcohol and carbon dioxide. But recently, biocatalysis has moved into very high-tech manufacturing. We use specific enzymes to make complex pharmaceutical drugs.
Why are they so good for that?
Because enzymes are incredibly picky. They have what's called selectivity. An enzyme might only react with one very specific molecule, and even only one specific mirror image of that molecule, ignoring everything else in the soup.
And I'm guessing they work under pretty mild conditions. No blast furnaces needed.
Usually, yes. They work in water at or near room temperature and normal pressure. They are the ultimate green catalyst in that sense. The downside is that they can be fragile. If you heat them up too much, they denature.
They cook, like an egg.
Exactly like an egg. They lose their shape and stop working.
So we have the players on the board. We know what they do and how they work. But I really want to shift to the impact. In the intro, we made this pretty bold claim that without one specific catalytic breakthrough, half the people listening right now, statistically speaking, wouldn't be alive.
That sounds like massive hyperbole.
It does, but it isn't.
Looking at the history of the Haber-Bosch process, the math actually checks out. It's astonishing.
It is not an exaggeration to say this is the single most significant industrial discovery in the history of our species. To understand why, we have to transport ourselves back to the year 1900.
Okay, set the scene for us. What was the world like? The world was approaching a cliff, a Malthusian cliff. The human population was growing rapidly, thanks to advances in medicine and sanitation. But our ability to grow food was hitting a hard wall. We were running out of nitrogen.
Now, this is the part that always confused me a bit. I remember from science class that the atmosphere is 78% nitrogen. We're literally breathing it in and out right now. How could we possibly be running out of it?
That is the cruel irony of nature. We are swimming in a vast ocean of nitrogen, but we can't drink the water. The nitrogen gas in the air, which is written as N2, is locked up. The two nitrogen atoms are held together by a powerful triple bond.
The triple bond, that sounds strong.
It is one of the strongest chemical bonds in all of nature. It's incredibly stable. And because it's so stable, it's inert. It doesn't want to break apart. It doesn't want to react with anything. And plants, which need nitrogen to build their DNA and proteins, they have no way to break that triple bond. They can't access that massive reservoir of atmospheric nitrogen.
So for all of human history, farmers had to get nitrogen from the soil.
Right. For centuries, they used manure or crop rotation with legumes that have special bacteria on their roots. Then, in the 19th century, we discovered massive deposits of naturally fixed nitrogen, things like saltpeter for the deserts in Chile or grano.
Which is bird droppings.
Yes, massive fossilized mountains of ancient bird droppings on islands in the Pacific. It was the best fertilizer on Earth because the nitrogen in it was already in a chemically accessible form for plants.
And nations actually fought wars over this stuff, didn't they? The guano wars.
Yeah, absolutely did. It was a strategic resource, just like oil is today. But by 1900, the guano was running out. The saltpeter mines were being depleted. Prominent scientists like Sir William Crookes were giving these very public, very dire speeches predicting global famine by the 1930s. They calculated that without a new source of nitrogen, millions, perhaps billions, would starve.
The classic Malthusian trap. Population outstripping resources.
Exactly. We desperately needed a way to pull nitrogen out of the air and turn it into something plants could use, like ammonia, which is NH3. But nobody could figure out how to break that triple bond without using insane, impractical amounts of energy.
Enter Fritz Haber.
In 1909, a German chemist named Fritz Haber finally did it. He built a device in his lab, a tabletop reactor, that could squeeze nitrogen and hydrogen gas together under extremely high heat and pressure, using a catalyst to force them to combine and make ammonia.
What was the catalyst that he used for that first proof of concept?
He used osmium.
Osmium. I don't think I've ever even heard of that.
You probably haven't. It's one of the rarest, densest metals on Earth. The entire world supply of osmium at that time was probably just a few kilograms. So Haber proved it was scientifically possible. But you couldn't feed the world with osmium. It was a laboratory curiosity, not an industrial solution.
So the science was there, but the engineering wasn't. The scaling was the problem.
That is where BASF, the huge German chemical company, came in. They saw the potential, bought the patent, and assigned a brilliant young engineer named Carl Bosch to scale it up. And this is where the story becomes a true testament to human stubbornness and industrial might.
Stubbornness is an understatement. I was reading about the famous 20,000 experiments.
Bosch and his chief chemist, Alwin Mitash, set up a high-throughput testing lab. They knew they needed a cheap, abundant catalyst. Iron seemed like a good candidate, but pure iron didn't work very well. It wasn't active enough.
So they just started mixing things in.
They started testing every combination they could think of. They took iron and they added a pinch of every other element on the periodic table. They tested thousands upon thousands of different formulations.
20,000 times. Is that a real number?
Over 20,000 individual experiments running different mixtures of iron with other elements under different conditions. Imagine the sheer grind of that work. Day after day, month after month, mostly failure after failure.
But eventually, they found it.
They did. They found the magic recipe. And it's a recipe we still use with some refinements to this day. It was iron, but it was promoted with small amounts of potassium, aluminum, and calcium.
I want to focus on this for a second because it circles right back to the Sabatier principle and how catalysts work. Why did adding a tiny pinch of potassium and aluminum make the iron work so much better? What were they actually doing at the atomic level?
It's absolutely fascinating. The potassium acts as what we call an electronic promoter. In simple terms, it donates some of its electron density to the nearby iron atoms. This changes the electrical charge of the iron surface just enough to help the nitrogen molecule stick better, and more importantly, it helps to weaken that incredibly strong triple bond.
So the potassium is like a chemical can opener. It loosens the lid on the jar.
That's a great way to put it. It destabilizes the nitrogen molecule just enough to let the hydrogen atoms come in and attack it.
Okay, so that's the potassium. What about the aluminum?
The aluminum and calcium are structural promoters. The Haber-Bosch process runs at about 500 degrees Celsius and over 100 times normal atmospheric pressure. It's brutal. At that heat, tiny iron particles want to melt and stick together. They want to clump up.
A process called sintering, right?
Sintering, yes. And if they clump up, you lose your surface area. Your porous sponge turns into a solid, useless brick. The reaction just stops. The aluminum oxide forms little spacers between the iron particles and physically prevents them from touching and merging. It keeps the catalyst fluffy and porous and active, even under those hellish conditions.
So the potassium makes it chemically active, and the aluminum makes it structurally durable. It's a team effort.
And that combination, found through sheer brute force experimentation, changed the world.
It really did. The numbers that flow from this are just hard to wrap your head around.
Today, the global network of Haber-Bosch plants produces about 174 million tons of ammonia every single year. That ammonia becomes synthetic fertilizer. That fertilizer is spread on fields and grows the crops that feed the world.
And here is the fact that I just keep coming back to. On average, half of the nitrogen atoms in your body right now, the nitrogen in your DNA, in your muscles, in your brain, at some point, it came from a Haber-Bosch factory.
We are, in a very literal and chemical sense, synthetic beings. We are part industrial chemistry. This single process supports roughly 40% of the entire global population. Without it, the Earth's natural nitrogen cycle could sustainably support maybe 4 billion people.
And we have 8 billion. The other 4 billion of us exist because of this catalyst.
We do.
That is awe-inspiring. It's one of the greatest stories of human ingenuity. But we have to look at the other side of the ledger. There's a steep cost to this miracle.
A massive environmental cost. Remember, I said they used extremely high heat and pressure.
500 degrees Celsius and over 100 atmospheres of pressure.
Maintaining those conditions requires burning a tremendous amount of fossil fuels, usually natural gas, which is used both for the energy and as the source of hydrogen. The Haber-Bosch process alone consumes between 1% and 2% of the world's entire annual energy supply.
That is a staggering statistic for a single chemical reaction.
And in doing so, it generates about 1.6% of all man-made CO2 emissions. It is a massive carbon bomb at the heart of our food system. We fixed the food crisis of the 20th century, but we contributed significantly to the climate crisis of the 21st.
And we can't really talk about Fritz Haber without acknowledging the dark complexity of his life and legacy. He won the Nobel Prize in 1918 for synthesizing ammonia for, as the citation says, the greatest benefit to mankind.
Bred from air.
Bred from air. But during World War I, he was also the father of modern chemical warfare.
Yes. He was a fervent nationalist, and he applied his brilliance to the German war effort. He personally oversaw the first deployment of chlorine gas as a weapon at the Second Battle of the Ypres. He used the same genius that fed the world to develop weapons that killed and maimed thousands in the trenches.
It's just a stark, chilling reminder that chemistry itself doesn't have a conscience. It's a tool.
It is the ultimate double-edged sword.
Yes.
But moving on from food, there was another parallel catalytic revolution that really defined the character of the 20th century. If Haber-Bosch gave us the quantity of life, this next one gave us the stuff of modern life.
You're talking about the plastic revolution.
Specifically, the discovery of what are called the Ziegler-Natta catalysts in the 1950s.
Now, hold on. We had some plastics before the 1950s, didn't we? Things like Bakelite or nylon.
We did, yes. But the common plastics we had, particularly polyethylene, were, well, they were mediocre. They were soft, they were waxy, or they were brittle. You couldn't make a sturdy bucket or a high-pressure water pipe out of them. They melted at very low temperatures.
Why were they so weak? What was the problem?
The problem was that the molecules were messy. A plastic is a polymer, which is just a long, long chain of repeating molecular units, or monomers. Before the 1950s, the way we made these chains used high pressure and things called free radicals. The result was chaotic. The chains had branches shooting off in all sorts of random directions.
I like the analogy in the research notes about the zipper.
It's a perfect analogy. Imagine trying to close a zipper where all the teeth are bent and twisted and pointing in random directions. You can't zip it up. The chains can't pack together neatly and tightly. And if they can't pack together tightly, the resulting material is weak and has a low melting point.
So how did Carl Ziegler and Giulio Natta fix the zipper?
They discovered a completely new class of catalyst, using mixtures of titanium compounds with organoaluminum compounds that didn't just speed up the polymerization reaction, it controlled it. It acted like a tiny scaffold or template.
A template? How do you mean?
As the polymer chain was growing, the catalyst would grab each new monomer unit and force it into a very specific orientation before allowing it to attach to the growing chain.
So it's not just building a brick wall, it's making sure every single brick is laid perfectly straight and aligned with the others.
Exactly. They achieved what's called stereoregularity. All the little side branches on the polymer chain were made to point in the same direction. This allowed the long chains to pack together beautifully into a dense crystalline structure.
Like stacking nice, flat pieces of lumber instead of a messy pile of twigs.
And suddenly, we had high-density polyethylene, or HDPE, and polypropylene. We could suddenly make durable milk jugs, car bumpers, strong ropes, surgical mesh, pipes that last for 50 years underground.
The Tupperware age was born.
The modern material world is built of this stuff. It also allowed synthetic rubber to finally be made with a molecular structure identical to natural rubber, which was a huge deal for things like vehicle tires. Ziegler and Natta shared the Nobel Prize in 1963, and they absolutely deserved it.
But again, here we are, facing the hangover from that revolution. We got really, really good at making plastic. Maybe a little too good.
We have produced about 8 billion tons of plastic since that breakthrough. And the vast, vast majority of it is still here, in landfills, in the oceans, in our environment.
And we recycle, what, less than 20% of it globally? And honestly, reading about mechanical recycling made me realize why that number is so low. It's not really a circle, is it? It's more of a downward spiral.
It is downcycling for the most part. If you take a plastic bottle, you chop it up into flakes, you melt it down, you try to make a new bottle, the heat and stress of that process degrades the plastic. The long polymer chains break. The material gets yellow and brittle.
So you can only do it once or twice.
Right, so usually you turn a high-quality bottle into a lower-quality product like a park bench or fibers for a carpet, and then the carpet eventually goes to the landfill. You can't turn a bottle back into a bottle indefinitely. The loop isn't closed.
Until perhaps now. This is where the research in our stack gets genuinely exciting. We're moving from making plastic to chemically unmaking it, catalytic upcycling.
This is the absolute frontier. The goal is to use catalysts to chemically chop those long polymer chains back into their original building blocks, the monomers, or, alternatively, into high-value liquid fuels.
Let's break down some of the techniques here, because this isn't just melting plastic down. This is like performing chemical surgery on it. Pyrolysis seems to be the big one.
Pyrolysis means heating the plastic in the complete absence of oxygen. If there's no oxygen, it can't burn. It just vibrates more and more violently from the heat until it falls apart. But if you just heat it without a catalyst, you get a useless, messy sludge, a whole soup of random molecules.
So you need a catalyst to guide the breakdown process, to control it.
Yes. And very often, they use zeolites, again, those porous mineral sponges we talked about. But here's the really clever trick. Zeolites have very specific, well-defined pore sizes. You can think of it like a molecular coin sorter.
Okay, I'm with you.
The catalyst only allows molecules of a certain size and shape to fit into the pores where the reaction happens.
Yeah.
So it forces the long, floppy plastic chains to break into very specific lengths. If you tune the pore size of your zeolite correctly, you can force the plastic to break down predominantly into molecules that are exactly the size of gasoline or diesel fuel.
So you can essentially turn a mountain of mixed plastic trash into a tank of high-grade liquid fuel.
With a high energy density, yes. It's a way to reclaim the chemical energy that's stored in that waste plastic.
There was another study that really caught my eye. It was about hydrocracking. They managed to turn plastic grocery bags into jet fuel.
This was a brilliant piece of work from a team using a ruthenium catalyst supported on zirconium oxide. It took polyethylene, your basic plastic bags, milk jugs, and reacted it with hydrogen under pressure.
Why add hydrogen into the mix?
The hydrogen helps to cap the ends of the broken chains so they remain stable fuel molecules. But the real key was the catalyst's selectivity. Usually when you chop up plastic this aggressively, you make a lot of methane.
Methane being natural gas.
It's a gas. It's a very low-value product. You don't want to make gas. You want to make high-value liquids. Liquids are much easier to store and transport, and they're worth more. This specific ruthenium catalyst was amazing because it was able to cut the long chains right in the sweet spot for jet fuel without shattering them all the way down to methane.
That is just incredible. Jet fuel from garbage. But I think my favorite concept in this whole section is solvolysis, because this actually sounds like the true infinite recycling loop we've always been promised.
Solvolysis is particularly effective for plastics like PT, the clear plastic used in water and soda bottles. What you do is you put the shredded plastic in a solvent, you heat it up a bit, and you add a catalyst. Sometimes simple things like zinc chloride or even just sodium hydroxide.
And it just dissolves.
It effectively unzips the polymer. It chemically breaks it back down into its original raw ingredients, terephthalic acid and ethylene glycol.
And if you purify those ingredients,
you get virgin quality material. You can then take those raw materials and make a brand new peat bottle that is chemically and physically identical to one made from crude oil. You can do this over and over and over again. It's a truly circular process.
That's the holy grail of recycling right there. But we can't ignore the biological angle. The enzymes are back.
The plastic-eating enzymes. This field is just exploding right now. It started when scientists found bacteria in Japanese trash gums that had naturally evolved on their own to eat peat plastic. The problem was they were very, very slow. They would take weeks or months just to eat a thin film.
So scientists decided to give them a gym membership and put them on a training program.
In a way, yes. They used a technique called directed evolution, which was pioneered by Francis Arnold, who won a Nobel Prize for it.
Yeah.
You take the gene that makes the enzyme, you intentionally cause random mutations in it, you create thousands of variants, and then you test them to see which ones eat plastic a little bit faster.
You take the winners and you mutate them again.
And again and again.
Yeah.
You were essentially speeding up evolution in a test tube.
And where are we now?
Now we have superenzymes that can break down a plastic bottle into its monomers in a matter of hours, not months. There's a company in France called Carbios that is doing this at a commercial scale. And the really cool thing about enzymes is their specificity. You can throw a dirty, mixed-up pile of textile waste in the vat, say, a polyester shirt that's blended with cotton and has dyes in it.
Which is a nightmare for any traditional recycling method.
It's impossible for traditional recycling.
Yeah.
But the enzyme only sees and eats the polyester. It completely ignores the cotton, it ignores the dye, it just liquefies the plastic component and leaves everything else behind, making it easy to separate.
It's precision chemical recycling.
It is. It's surgical.
Okay, so we have these incredible new tools in our toolbox. Zeolites, ruthenium catalysts, super enzymes. But here's the bottleneck. Finding these new materials is still hard. Remember Bosch and his team? 20,000 experiments. That took years. We don't have decades to solve the plastic crisis or the climate crisis. This brings us to the modern twist of this whole discussion. We are bringing in the heavy hitters. Artificial intelligence.
We're finally shifting from that old paradigm of trial and error to a new one of rational design.
I was reading about a project from Google's DeepMind called GNOME, that's G-N-O-M-E, for graph networks for materials exploration. The numbers involved here are they're silly, they're hard to comprehend.
They are absolutely astronomical. What DeepMind did was train a powerful AI on the fundamental laws of physics and chemistry and all known crystal structures. Then they essentially asked it to dream up new, stable chemical combinations.
And it didn't just dream up a few hundred.
It identified 2.2 million new potential materials. And crucially, it predicted that 380,000 of them would be thermodynamically stable, meaning they should be possible to actually synthesize in a lab.
Context is so important here. How many stable crystal structures did we as a species know about before this project?
About 48,000. Discovered over centuries of work.
So in a matter of months, they increased the total of human knowledge of stable materials by a factor of 10.
They did. In a few weeks of pure computing time, they basically mapped out an entirely new, expanded periodic table of possible combinations.
But are these just digital fantasies sitting on a server somewhere, or are they actually useful?
Oh, they are potential gold mines. Out of that data set, they've already identified 528 potential new lithium-ion conductors that could lead to better, safer solid-state batteries. They found thousands of new potential catalysts for things like splitting water to make hydrogen or reducing CO2 into fuels.
So instead of a scientist just randomly mixing metals together in a lab like Bosch did, they can now look at this AI-generated treasure map and say, that specific structure looks like it has the perfect properties for the reaction I care about.
Exactly. It narrows the search space from near infinity down to a manageable list of promising candidates. It's a revolution in how we discover materials.
And it's not just about finding new materials, it's also about reading the old science.
Nah.
We've all played with things like ChatGPT, but a specialized model called Catalysis seems to be on a whole other level.
Think about the problem of scientific literature. There are millions and millions of academic papers published on catalysis. No single human could ever read them all, or even a fraction of them. A researcher might be struggling with a problem in 2024, not realizing that a clue to the solution was published in an obscure Polish chemistry journal back in 1970.
The needle in a global haystack.
Yeah, right. CattleGPT is an AI that has been trained to read and understand all of that literature. It extracts the recipes. It learns the connections between different materials and reaction outcomes. So now a chemist can just ask it a question in plain English. I want to oxidize methane using an iron-based catalyst, but I need to avoid high pressure. The AI can synthesize the knowledge of 10,000 papers and say, Based on the literature, you should try this specific formulation promoted with these elements. It has a high probability of success.
It's like having a senior research assistant who has a perfect photographic memory of the entire Library of Alexandria.
And then the final step is to connect that AI brain to a physical body. This is where high-throughput experimentation comes in.
The robotic labs.
Yes. You have the AI predict 100 promising catalyst candidates. It sends the instructions to a robot. The robot automatically mixes the chemicals in tiny wells, heats them, passes gas over them, and tests the results with sensors. It does this 247. It feeds all that new data back to the AI.
And the AI learns from the results, adjusts its models, and then designs the next 100 experiments.
And the robot doesn't sleep. It doesn't take coffee breaks. It doesn't get discouraged after failure number 500 in a row. It accelerates the cycle of discovery from something that used to take 10 to 20 years down to a matter of months. It's terrifyingly efficient.
So with these new super brains and robotic arms, what are we actually looking for? What are the future frontiers of catalyst design? The notes mention something called high-entropy alloys. This sounds chaotic by design.
It is chaos, but it's a very controlled and useful kind of chaos. Traditional alloys that we're all familiar with, like steel or bronze, are usually one main base metal with a tiny pinch of something else added in.
The soloist and the backup singers.
A great way to put it. High-entropy alloys, or HEAs, are completely different. They're a mix of 5 or more different elements, all mixed together in near equal proportions.
So it's not a soloist, it's a jazz ensemble where everyone is trying to play lead at the same time.
I like that analogy. And because you have 5 or more different types of atoms all jumbled together on the surface of this metal is incredibly complex. It's not a uniform flat plane like a pure metal. It's a rugged, diverse landscape of different atomic neighborhood.
Why is that a good thing? I thought for things like the plastic catalysts, we wanted perfect order.
In this case, that diversity becomes a huge strength. Remember the Sabatier principle, the Goldilocks zone. In a simple pure metal, you usually have a frustrating trade-off. If you change the metal to make it bind reactant A a little bit better, it almost always makes it bind reactant B a little bit worse. These are called scaling relations. You're stuck. You can't have your cake and eat it too.
You're stuck on a chemical seesaw. Pushing one side down makes the other go up.
But on a high-entropy alloy, you have millions of different unique active sites on the surface. You might find one little spot where 3 specific atoms, say cobalt, nickel, and copper, come together in a unique triangle that is absolutely perfect for step 1 of a reaction. And right next to it, you might find a different arrangement that is perfect for step 2.
So you can break the seesaw. You can potentially tune the surface to do multiple previously impossible things at once.
Exactly. It opens up an entirely new dimension of catalyst design. It allows us to escape those old limitations.
And then on the complete opposite end of the spectrum from these messy, complex alloys, we have single-atom catalysts.
This is the ultimate play for efficiency and cost-effectiveness. We talked about supported nanoparticles earlier, sprinkling platinum dust on a high-surface area sponge.
Right, to get more bang for your buck. But even in a tiny dust particle, there are still atoms stuck on the inside that are doing nothing.
Correct. Single-atom catalysis is exactly what it sounds like. You use sophisticated chemistry to anchor individual, isolated metal atoms onto a support material. There are no particles, just single atoms spaced out.
So every single atom of your precious metal is a working active site.
100% atom economy. You waste absolutely nothing. If you're using fantastically expensive metals like platinum or iridium or rhodium, this is the only way to make the economics work for massive scale applications like green hydrogen production.
Let's wrap up by connecting all of this to the big picture, the global energy transition. We all know we need to get off fossil fuels. We want to power the world with wind and solar, but the sun doesn't always shine and the wind doesn't always blow.
And that intermittency is a huge, huge problem for our old friend, the Haber-Bosch process.
Yeah.
Those giant centralized chemical plants hate fluctuation. They're designed to run at a perfectly steady state, 2047, for years at a time.
Yeah.
You can't just turn them off when a cloud goes over the solar panel and turn them back on again. They would clog up, or worse.
So if we really want to make green ammonia, that is, fertilizer made using renewable energy, we need a completely new engine, a new catalyst.
We need catalysts that are much more flexible. We need new materials that can operate efficiently at lower temperatures and pressures, and that can handle the ups and downs of an intermittent power supply from renewables.
And this leads to this really exciting idea of distributed production.
This is a beautiful and potentially world-changing concept. Instead of having one massive multi-billion-dollar factory on the coast somewhere shipping fertilizer all over the world, imagine a small shipping container-sized reactor sitting on a farm in Iowa or in a village in Kenya.
And it has a solar panel or a small wind turbine on the roof.
Exactly. It uses that renewable electricity to split water to get hydrogen. It pulls nitrogen from the air. And it uses these new advanced flexible catalysts to make just enough ammonia fertilizer for that local farm or that local community.
You completely decouple food security from volatile global supply chains. No more worrying about wars or blockades in shipping lanes cutting off a country's fertilizer supply.
It creates incredible resilience. And that brings us right to the final thought here: geopolitics.
Right. We are used to thinking of physical resources, oil, natural gas, coal, rare earth minerals, as the primary strategic assets. If you have the oil, you have the power.
But in a future world of circular chemistry and renewable energy, the catalyst is the strategic asset.
Walk me through that logic.
If you invent and control the patent for the best, most efficient catalyst for splitting water to make green hydrogen, you effectively control the future energy market. If you have the best catalyst for making green ammonia, you control global food prices. If you have the catalyst that turns mixed plastic waste into jet fuel more cheaply than anyone else, you control the future of materials.
So you don't need to dig holes in the ground and extract things anymore. You just need the intellectual property, the recipe.
The catalyst market itself is currently valued at about $44 billion. That sounds like a lot, but it's absolute peanuts compared to the trillions and trillions of dollars of economic value that it unlocks. It is the ultimate leverage point.
It's the key that opens every other lock.
We are moving away from an economy of extraction, digging things up and burning them, to an economy of synthesis and circularity. And the catalyst is the fundamental tool that makes that entire transition possible.
And if we can truly perfect that circularity, if we can close the carbon loop, turn waste plastic back into fuel or virgin plastic, and maybe even turn CO2 from the air back into useful fuels and products, we essentially solve the entire industrial pollution problem. We stop taking ancient carbon out of the Earth's crust. We just learn to efficiently cycle the carbon that's already up here in the biosphere with us.
That is the grand vision. We have the tools, we have the AI to accelerate discovery, we have the nanotechnology to build these materials atom by atom. Now it is just a matter of engineering, investment, and deployment at scale.
It really is a hopeful vision, and it's a very, very long way from relying on bird droppings and the brute force trial and error of the early 1900s.
It is indeed. The silent engine is finally getting a 21st century upgrade.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content, and support us on Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.